Picture a universe so dark and empty that not a single star flickered in the void. No galaxies, no planets, no light, just an endless sea of blackness stretching in every direction. This was our cosmos over 13 billion years ago, a place where the aftermath of the Big Bang had faded into silence, leaving behind only the faintest whispers of matter drifting through the cold. Then something extraordinary happened. A spark ignited in the darkness. The very first stars flared to life, and with them, the universe as we know it began to take shape. But how? What cosmic alchemy transformed that primordial emptiness into a canvas of light? The birth of the first stars isn't just a scientific mystery, it's the origin story of everything. Without them, there would be no planets, no elements, no life. They were the architects of the cosmos, forging the building blocks of reality itself in their fiery cores. Yet for all their importance, these ancient giants remain shrouded in mystery. How did they form in a universe that had never known starlight? What forces conspired to pull together the first fragile clouds of gas and ignite the dawn of creation? The answers lie buried in the deepest reaches of time, waiting to be uncovered. This is a journey back to the very beginning, to a moment when the universe was young and the rules of physics were still writing themselves. We'll explore how gravity sculpted the first structures in the cosmos, how darkness gave way to light, and how the echoes of those primordial stars still resonate in the atoms of our bodies today. By the end, you'll see the night sky differently, not just as a collection of distant lights, but as a living chronicle of the universe's earliest moments. So let's step into the darkness together and discover how the first stars lit up the cosmos, forever changing the story of existence. The universe's first moments were anything but quiet. In the searing heat just after the Big Bang, a swirling ocean of plasma, a superheated soup of particles filled all of space. Protons and electrons danced wildly, too energetic to combine, scattering light relentlessly in every direction. For nearly 400,000 years, photons couldn't travel more than a fraction of an inch before being knocked off course, making the cosmos opaque, like a fog so thick you couldn't see your own hand. Then, as the universe expanded and cooled, something pivotal happened. Electrons finally slowed enough to latch onto protons, forming the first hydrogen atoms in an event cosmologists call recombination. With that, the cosmic fog lifted. For the first time, light could travel freely across space, but there was no light to see. No stars, no galaxies, just an unimaginable void stretching endlessly in every direction. This was the beginning of the cosmic dark ages, a period of profound silence lasting hundreds of millions of years. The universe had structure, now vast, wispy clouds of hydrogen gas drifting through the darkness, but without stars to ignite them. These primordial ingredients lay dormant, like unlit kindling waiting for a spark. Gravity was the unseen hand shaping everything. Tiny fluctuations in density, left over from the Big Bang's quantum whispers, began pulling matter together ever so slowly. Where gas clustered slightly thicker, gravity grew stronger, drawing in more material over eons. These were the seeds of the first star's regions, so dense they collapsed under their own weight, heating up until the very atoms at their cores could no longer resist. When temperatures soared past 10 million degrees, hydrogen nuclei smashed together in a process called fusion, unleashing torrents of energy, and just like that, the darkness ended. But these weren't stars like the ones we know today. They were behemoths, hundreds of times more massive than our sun, burning ferociously bright and dying young in spectacular supernovae. Their explosive death scattered heavier elements, carbon, oxygen, iron into the void, the very materials that would later form planets and life. The Dark Ages had given way to dawn, and with it, the universe took its first step toward becoming the vibrant, star-filled expanse we see now. At the dawn of time, the universe's recipe was astonishingly simple. Just 3 ingredients stirred into existence by the Big Bang itself: hydrogen, the lightest and most abundant element, made up nearly 75% of this cosmic broth. Helium followed close behind, accounting for almost all the rest, and then there were mere traces of lithium, sprinkled so thinly they were like a pinch of salt in an ocean. That was it. No carbon, no oxygen, no iron, none of the elements that would later become the foundation of planets and life. This sparse, elemental purity was both a constraint and a gift. Hydrogen, in particular, held the key to the universe's future. Its single proton and electron made it the perfect fuel for the first stars. When squeezed under immense gravity, hydrogen atoms could fuse together, releasing staggering amounts of energy in the process. But here's the catch. This fusion required conditions so extreme they didn't exist right after the Big Bang. The early universe was still too hot and too uniform, its matter too evenly spread out. For stars to ignite, space needed pockets of imbalance, regions where gravity could gain a foothold and start pulling matter together. That's where quantum physics entered the stage. In the first fraction of a second after the Big Bang, microscopic fluctuations in energy density left faint ripples in the fabric of spacetime. These ripples, incredibly subtle at first, became the scaffolding for cosmic structure. Slightly denser patches of hydrogen and helium attracted more gas over millions of years, growing heavier and hotter until they crossed a critical threshold. Only then, in the heart of these collapsing clouds, could temperatures soar high enough to smash hydrogen nuclei together and spark fusion. Helium played a quieter but equally vital role. Though it couldn't fuse as easily as hydrogen under these early conditions, its presence altered how heat moved through these primordial gas clouds, influencing when and where they fragmented into star-forming clumps. Even the whisper-thin traces of lithium had an impact, acting as a cosmic coolant that helped gas clouds shed energy and contract faster. Together, these three elements set the stage for a revolution, one that would transform the universe from a dark, featureless expanse into a glittering tapestry of light. Gravity didn't work alone. It had help from the universe's own imperfections. In the aftermath of the Big Bang, space wasn't perfectly smooth. Imagine blowing on the surface of a steaming cup of coffee and watching tiny ripples form. Those ripples, but on a cosmic scale, were the subtle density variations imprinted in the early universe. Some regions held just a fraction more hydrogen than others, not enough to notice at first, but over time, these minute differences became gravity's foothold. Picture a vast, invisible web stretching across the cosmos, its threads woven from those slight overdensities. Gas didn't rush into these regions all at once. Instead, it was a slow, relentless pull, like a pendulum swinging in slow motion. Over millions of years, gravity coaxed atoms closer, millimeter by millimeter, until what began as a faint whisper of matter grew into a deep, resonant hum. The denser these pockets became, the stronger their gravitational pull, creating a feedback loop that fed on itself. Yet this process wasn't without friction. Heat and pressure pushed back, resisting collapse. The gas was stubborn. It needed to shed energy to condense further. And in a universe without stars, the only way to cool was through the faint glow of hydrogen atoms releasing photons. This cooling was agonizingly slow, like waiting for a campfire to die down ember by ember, but gravity had time on its side. Eventually, the gas grew so dense that even this feeble cooling couldn't stop the inevitable. And then came the tipping point. When a cloud reached a critical mass, its core could no longer support its own weight. Like a bridge buckling under too much strain, it collapsed inward in a runaway chain reaction. Temperatures skyrocketed as particles packed tighter, friction turning the core into a seething furnace. At 10 million degrees, hydrogen nuclei finally overcame their natural repulsion and fused, igniting the first thermonuclear flame in the cosmos. This was gravity's masterpiece, a balancing act between collapse and resistance, stretched across eons. Those initial ripples, barely more than mathematical ghosts, had set the stage for the universe's first light. Without them, matter might have remained adrift forever, never coalescing into the stars that would later forge the elements of life. It was a dance of patience and precision, one that transformed the void into a cradle for everything that followed. Hidden in the cosmic shadows, an invisible force was quietly reshaping the universe long before the first stars flickered to life. Dark matter, mysterious, elusive, and utterly unlike anything we can see, played the role of a cosmic architect, weaving the gravitational framework that would make starlight possible. While ordinary matter, the hydrogen and helium that filled the early cosmos, was busy jostling with radiation and heat, dark matter remained unaffected, its particles indifferent to light's push and pull. This indifference gave it a critical advantage. It could start clumping together immediately after the Big Bang, forming vast, ghostly structures that would later guide the birth of the first stars. Think of dark matter as the scaffolding of an unfinished skyscraper. Long before the steel beams and glass panels, the visible universe take shape, this unseen framework defines the entire structure. In the same way, dark matter's gravitational wells acted as cosmic traps, funneling ordinary gas into denser and denser pockets. Without this hidden guidance, hydrogen might have drifted aimlessly for far longer, delaying star formation by billions of years. But dark matter's patient, relentless pull ensured that gas had somewhere to gather, a gravitational anchor in an otherwise featureless void. The numbers are staggering. For every particle of ordinary matter in the early universe, there were at least 5 times as many dark matter particles. Though they didn't collide or emit light, their collective gravity sculpted the cosmos on the grandest scales. Simulations of the early universe show this process in action, dark matter forming sprawling, web-like filaments, with ordinary matter streaming along these invisible highways, pooling at the intersections like water collecting in a basin. It was at these cosmic crossroads where dark matter's pull was strongest that the first protostars began to take shape. Yet dark matter's influence didn't stop there. By accelerating the collapse of gas clouds, it also helped overcome one of the universe's greatest obstacles to star formation: heat. As hydrogen atoms crowded together, they grew hotter, creating pressure that resisted further collapse. But dark matter's extra gravitational squeeze forced the gas to condense faster than it could push back, reaching the critical temperatures needed for fusion in a fraction of the time. In essence, dark matter turned up the furnace, igniting the first stars in an era that might otherwise have remained cold and dark. Even now, we see the legacy of dark matter's invisible hand in the way galaxies spin, in the way light bends around cosmic voids, and in the very structure of the universe itself. The first stars were not just born from gas, they were born from the marriage of visible and invisible forces, a partnership that lit the cosmic dark and set the stage for everything to come. The transformation from a cold, drifting cloud of gas into a blazing star begins with a whisper, not a bang. Deep within those ancient hydrogen reservoirs, gravity's pull grew stronger by the eon, drawing atoms closer until the gas became so dense it fragmented into clumps, each one a potential stellar womb. These weren't the orderly spheres we imagine today. They were chaotic, turbulent knots of matter, spinning and collapsing in a cosmic dance. As gravity tightened its grip, the cores of these clumps grew hotter, their particles colliding with frenetic energy. Friction turned kinetic energy into heat, and temperatures began rising first by hundreds, then thousands, and finally millions of degrees. But heat alone couldn't ignite a star. For fusion to begin, the core needed to reach a critical threshold where hydrogen nuclei could overcome their natural repulsion, a feat requiring temperatures hotter than the sun's surface today. The gas fought back, its pressure pushing outward like an overinflated balloon resisting collapse. Yet gravity always won in the end, compressing the core further until the atoms had no escape. Electrons were stripped from their nuclei, creating a seething plasma, and at 10 million degrees, the first proton-proton collisions sparked. This was the moment of creation. Hydrogen nuclei fused into helium, releasing a torrent of energy in the process. The outward pressure from this nuclear firework finally balanced gravity's inward crush, stabilizing the protostar in a precarious equilibrium. The first true star had awakened, its light piercing the cosmic dark for the very first time. Yet these newborn stars weren't gentle. They were ravenous behemoths, consuming their surrounding gas with voracious intensity, growing larger and hotter as they fed. Their cores burned so fiercely that some reached sizes and luminosities unimaginable today, stars hundreds of times more massive than our Sun, living fast and dying young in colossal explosions. The birth of a star wasn't a solitary event. Across the early universe, countless protostars flared to life in cascading waves, each ignition sending ripples through nearby gas clouds, triggering new collapses in a chain reaction of stellar genesis. This wasn't just the birth of individual stars, it was the awakening of the cosmos itself, a transition from darkness to light that would forever alter the universe's destiny. And at the heart of it all lay a simple, elegant truth. Stars weren't just objects in space. They were the universe's way of turning simplicity into complexity, darkness into brilliance, and raw ingredients into the building blocks of everything to come. The first stars weren't just ancient. They were utterly alien compared to anything shining in our night sky today. Known as Population 3 stars, these primordial giants defied the rules that govern modern stellar life. Picture a star so massive it makes our Sun look like a pebble beside a mountain. These cosmic titans formed from nothing but hydrogen and helium, the only elements available in the early universe's sparse pantry. Without heavier elements to seed their birth or regulate their growth, they ballooned to sizes we can barely comprehend, some reaching hundreds of times the mass of the Sun. Their purity shaped everything about them. Modern stars like ours are polluted rich with traces of carbon, oxygen, and iron recycled from generations of stellar explosions. These heavier elements act like cosmic brakes during star formation, helping gas clouds cool and fragment into smaller, more stable clumps, but the first stars had no such luxury. Their gas clouds lacked these cooling agents, forcing them to collapse into monolithic structures too colossal to sustain themselves for long. The result? Stars that burned brighter and hotter than anything since, their surfaces blazing with ultraviolet light intense enough to strip electrons from atoms light years away. And their lives were shockingly brief. While a star like our Sun can burn steadily for billions of years, Population 3 stars lived fast and died young. Some lasted just a few million years, a cosmic blink before collapsing under their own weight in cataclysmic supernova, or even vanishing into black holes without a trace. Their deaths were anything but quiet. These explosions scattered the first heavy elements into the void, seeding future generations of stars and planets with the building blocks of complexity. Yet despite their brilliance, we've never seen one directly. Their light faded eons ago, stretched into infrared whispers by the expanding universe. Everything we know comes from intricate computer simulations and the faint chemical fingerprints they left behind in later stars. Studying them is like reconstructing a dinosaur from a single tooth, except the tooth is made of primordial gas, and the dinosaur could outshine entire galaxies. What's most fascinating isn't just how different they were, but how their existence made our universe possible. Every atom in your body heavier than hydrogen and helium was forged in stars, but without those first, unimaginable giants, there would have been nothing to start the cycle. They were the ultimate pioneers, transforming a sterile cosmos into a chemical playground ripe for planets, life, and eventually, creatures curious enough to unravel their story. Their legacy isn't just in the past, it's in the air you breathe, the iron in your blood, and the very screen you're staring at right now. Monsters of the cosmos, that's the only way to describe the first stars. These weren't just larger than our Sun, they dwarfed it on a scale that's almost incomprehensible. Picture a star so massive it could swallow our entire solar system without breaking a sweat. its surface radiating heat so intense it would vaporize any known material in seconds. Current theories suggest these behemoths ranged from 100 to 1,000 times the mass of the Sun, making even the most massive stars we observe today look like flickering candles next to a bonfire. The sheer size of these ancient giants wasn't just for show, it dictated every aspect of their existence. Unlike modern stars, which often form in clusters with a mix of sizes, the first stars were solitary titans, born from gas clouds too uniform to fragment into smaller siblings. Without heavier elements to help cool and condense the gas, these clouds collapsed into single, monstrous cores, growing larger and hotter until fusion ignited in a furious blaze. Their cores burned at temperatures exceeding 100 million degrees, driving nuclear reactions so violent they would make a supernova seem tame by comparison. But such enormity came at a cost. The lifespan of a star is inversely tied to its mass. The bigger it is, the faster it burns through its fuel. While a star like our Sun can shine steadily for billions of years, these primordial leviathans lived lives of breathtaking brevity. Some lasted just 2 or 3 million years, a mere heartbeat in cosmic time before meeting spectacular ends. When their cores ran out of hydrogen, they didn't fade gently. Instead, they collapsed under their own weight, triggering supernovae so powerful they could outshine entire galaxies for weeks. Others might have skipped the explosion entirely, their cores imploding directly into black holes without warning, vanishing from the universe as suddenly as they appeared. What's even more astonishing is how these deaths shaped everything that followed. The explosions of the first stars didn't just vanish into the void, they scattered the universe's first heavy elements into the surrounding gas. Carbon, oxygen, silicon, and iron, forged in their cores, were hurled into space, enriching the cosmos with the raw materials needed for rocky planets, organic molecules, and eventually life itself. In a very real sense, the brevity of their lives was the reason ours became possible. Yet for all their significance, population 3 stars remain elusive. No telescope has ever captured their light directly. Their era ended so long ago that their photons have stretched into infrared oblivion. Instead, we piece together their story from the chemical fingerprints they left behind in younger stars, or the faint echoes of their explosions imprinted on the cosmic microwave background. They're ghosts in the data, cosmic legends written in the language of isotopes and gravitational waves. But perhaps the most humbling thought is this: if one of these monsters existed in our galaxy today, its sheer brightness would render every other star invisible to the naked eye. Its ultraviolet radiation would sterilize planets light years away, and its death throes would light up the sky like a second sun. We owe our existence to these unimaginable giants, yet we'll never see their like again. The universe has moved on, trading raw power for longevity, and in that trade-off it created the conditions for us to exist, to look up at the night sky and wonder about the dawn of light itself. For hundreds of millions of years, the universe was a silent, lightless expanse, a realm where hydrogen atoms drifted through endless night. Then, in scattered pockets across the void, the first stars blazed to life and everything changed. Their birth didn't just illuminate the darkness, it tore through the fabric of the cosmos itself. Ultraviolet radiation, fierce and unrelenting, poured from their surfaces like floodgates opening, smashing apart the very atoms that had taken eons to form after the Big Bang. This was reionization, the universe's second great transformation, a violent rebirth that would shape the fate of all existence. Imagine a fog so thick it blankets everything, then suddenly, countless superheated lighthouses switch on all at once. The first stars, those massive, short-lived giants, acted like cosmic blowtorches, their intense ultraviolet light stripping electrons from hydrogen atoms in vast bubbles around them. One by one, these ionized regions grew, merging over time until the entire universe became transparent again, though now for an entirely different reason. Where recombination had allowed light to travel freely by forming neutral atoms, reionization cleared the stage for starlight to persist across cosmic distances, forging the luminous universe we recognize today. The scale of this upheaval is staggering. Each of those early stars could ionize hydrogen for thousands of light-years in every direction. Unlike modern stars, which often cluster and shield one another's radiation, these solitary titans had no neighbors to absorb their fury. Their photons traveled unimpeded, carving out spheres of influence that grew with each generation of stars. By the time the universe reached its billionth birthday, nearly all the hydrogen in existence had been torn apart once more, not by heat but by starlight itself. Yet reionization wasn't instantaneous. It unfolded in fits and starts, a patchwork of light and shadow as stars ignited and died across the cosmos. Some regions were blasted clear early on, while others lingered in darkness until later waves of star formation reached them. This inconsistency left imprints in the cosmic microwave background, subtle variations in polarization that telescopes like Planck have detected, offering us a roadmap of the universe's awakening. What's often overlooked is how fragile this transition was. Had the first stars been slightly less massive or slightly dimmer, reionization might have dragged on longer, delaying the formation of galaxies and altering the chemistry of the cosmos. Instead, their overwhelming power set the universe on a fast track to complexity. The ultraviolet photons that ripped atoms apart also provided the energy needed to drive chemical reactions in emerging molecular clouds, paving the way for richer chemistry in future stellar generations. But there's a beautiful irony here. The same radiation that ended the Dark Ages also made them permanently unobservable to us. Those early epochs before starlight are now hidden behind a curtain of ionized gas, a curtain those first stars themselves drew shut. To peer further back, astronomers must rely on indirect clues: the faint afterglow of the Big Bang, the shadowy absorption lines of ancient quasars, or the whispers of hydrogen still untouched by starlight at the universe's edges. This paradox defines our cosmic history. Light emerged from darkness by destroying the very conditions that birthed it, leaving behind a universe so transformed that its origins are written in ghosts and echoes. The first stars didn't just shine, they remade reality, turning a neutral, opaque cosmos into an ionized, transparent one. And in doing so, they laid the groundwork for everything that followed: galaxies, planets, and ultimately, beings capable of looking up and wondering how it all began. The demise of the first stars wasn't an ending. It was the universe's first act of cosmic alchemy. When these primordial giants exhausted their hydrogen fuel, their deaths were anything but quiet. Imagine a detonation so violent it could outshine an entire galaxy, hurling newly forged elements into the void at nearly the speed of light. Supernovae became nature's ultimate recyclers, transforming simple hydrogen and helium into a periodic table's worth of heavier elements: carbon, oxygen, silicon, and iron, before scattering them like seeds across the cosmos. For the first time, the universe had something more complex to work with. These heavier elements didn't just float aimlessly, they coalesced into vast molecular clouds, richer and more chemically diverse than the pristine gas that birthed the first stars. This was the critical turning point. Where population 3 stars had formed from featureless hydrogen, the next generation had access to metallic dust, tiny solid particles that could radiate heat away more efficiently, allowing gas clouds to fragment into smaller, more stable clumps. The result: stars that were smaller, cooler, and far longer lived than their massive predecessors. The numbers speak volumes. A single supernova from one of those early behemoths could enrich a gas cloud with enough heavy elements to form thousands of sun-like stars. Over generations, this process built up the chemical diversity we see today: oxygen for water, carbon for organic molecules, iron for planetary cores. Without those initial stellar explosions, Earth would literally not exist. The calcium in your bones, the silicon in rocks, even the gold in your jewelry, all were forged in the hearts of stars that died billions of years before our solar system took shape. But the recycling didn't stop there. Elements ejected by supernova became the raw materials for protoplanetary disks, swirling rings of gas and dust where planets formed. Some heavier atoms even bonded into complex molecules in interstellar space, creating the precursors to life long before Earth existed. Recent observations of distant quasars reveal telltale absorption lines from magnesium and iron in clouds over 12 billion years old, proving this enrichment began astonishingly early. Perhaps most remarkably, we're still witnessing this process today. In nearby stellar nurseries like the Orion Nebula, we can see young stars surrounded by the same heavy elements that their ancestors created. The cycle continues. Stars live, die, and scatter their remains to birth new generations in an unbroken chain stretching back to those first unimaginable explosions. Every time you take a breath, you're inhaling atoms that were once part of a star that died when the universe was young. The cosmos remembers its past not in history books but in the very fabric of matter itself. Unlocking the secrets of the first stars would be impossible without the power of modern supercomputers, machines capable of recreating the primordial universe inside lines of code. These simulations aren't just mathematical abstractions, they're time machines transporting us back to an era when gravity first coaxed hydrogen into the shapes of stars. Every calculation is a brushstroke painting a portrait of cosmic dawn, revealing details no telescope could ever glimpse directly. The process begins with the raw ingredients, a digital universe filled with pristine hydrogen and helium, its density variations mapped to the faint imprints left by quantum fluctuations in the Big Bang's aftermath. Supercomputers like NASA's Pleiades or Japan's Fugaku then apply the laws of physics at scales both vast and microscopic, tracking how gravity amplifies those subtle ripples over millions of years. Gas swirls, collapses, and fragments, all rendered in equations that would take centuries to solve by hand. The result, stunning visualizations showing tendrils of gas knitting themselves into knots, glowing brighter as they tighten until suddenly ignition. A virtual star flickers to life on screen. What these simulations reveal is astonishing. The first stars didn't form in isolation but in sprawling cosmic watersheds, where rivers of gas flowed along dark matter's invisible filaments. Some models suggest these stars emerged in pairs or small groups, bound together in gravitational dances before one grew dominant. Others show solitary leviathans, their birth triggered by shockwaves from nearby collapses. The finer details like rotation speed or magnetic field strength can mean the difference between a star that burns steadily and one that tears itself apart in violent bursts. One breakthrough came when researchers realized how light influenced the first star's formation. Early simulations assumed total darkness, but updated models include the faint glow of molecular hydrogen, a coolant that allowed gas to fragment more efficiently. This tiny adjustment birthed stars only 30 to 100 solar masses, not the 1,000-sun monsters once hypothesized. It's a reminder of how delicate the cosmic balance was. Change one variable, and the universe's first light might have looked radically different. The most breathtaking simulations don't stop at birth, they follow these stars to their explosive ends. Some collapse directly into black holes, their outer layers vanishing without a supernova. Others detonate in hypernova, blasting jets of material at near light speed and seeding galaxies with their elemental ashes. Each outcome leaves a distinct chemical fingerprint, and by comparing these virtual signatures to ancient metal-poor stars in our own galaxy, astronomers can test which models align with reality. Yet even the most advanced simulations have limits. They can't yet capture the turbulent chaos of star formation down to the atomic level, or the wild-card influence of dark matter microhalos. That's where projects like the James Webb Space Telescope come in. Its infrared eyes might spot indirect clues like the shadows of primordial gas clouds or the afterglow of early supernova. giving simulators new data to refine their digital universes. What's remarkable isn't just how far these simulations have come, but how they've reshaped our understanding of cosmic beginnings. By rewinding the universe in silicon, we've learned that the first stars weren't just bigger, they were stranger, more dynamic, and more influential than anyone imagined. They didn't simply light up the dark, they set the rhythm for everything that followed, their echoes written in the spin of galaxies, the chemistry of planets, and even the atoms in our hands. Every new simulation peels back another layer, revealing just how much the universe's fate hinged on those first fleeting sparks. Catching the faint echoes of the first stars isn't just a challenge, it's like trying to hear a whisper across 13 billion years of cosmic noise. That's where the James Webb Space Telescope, humanity's most powerful time machine, comes in. While we'll never directly observe those primordial giants, their light long since stretched into oblivion. JWST hunts for their fingerprints in the next best thing, the ancient galaxies and quasars they helped create. Imagine sifting through the ashes of a campfire to reconstruct the logs that burned. JWST does something similar, analyzing the chemical makeup of the universe's oldest galaxies to trace the elements forged by the first stars. When those early behemoths exploded, they polluted their surroundings with heavy elements, leaving a telltale signature in the gas clouds that formed subsequent generations of stars. By studying galaxies that existed just a few 100 million years after the Big Bang, JWST infrared eyes can detect these subtle chemical imbalances, like finding traces of smoke in a fossilized tree. One of its most powerful tools is spectroscopy, splitting light into its component colors to reveal hidden details. When distant quasar light passes through primordial gas clouds, certain wavelengths get absorbed, creating dark lines in the spectrum. These lines act as barcodes, encoding which elements are present. If JWST spots clouds with barely any heavy elements, it could mean they're being illuminated by light from population 3 stars nearby, stars so pure they'd leave almost no metal traces behind. But the real jackpot would be finding galaxies stuck in a transitional phase, ones where the first stars had just begun dying but hadn't yet enriched their surroundings fully. These rare systems would show bizarre chemical ratios, like lots of helium but almost no carbon, a hallmark of supernova from ultra-massive stars. In 2023, JWST spotted a candidate, a galaxy named Glass Z13, whose light dates back to just 300 million years after the Big Bang. Its strange brightness pattern hints at being powered by stars unlike any we see today, possibly the direct descendants of the first generation. Quasars, the brilliant cores of early galaxies, offer another clue. Their light sometimes passes through clouds of pristine gas untouched by stars since the Big Bang. By comparing these untouched clouds to ones slightly enriched with metals, astronomers can piece together how quickly the first stars polluted the cosmos. It's like comparing clean snow to slush. The difference tells you how long the storm has been raging. Perhaps the most thrilling possibility is catching the aftermath of a population 3 supernova in action. JWST infrared sensitivity lets it peer into dust-shrouded regions where these explosions might leave distinct chemical scars. Unusual ratios of elements like neon and oxygen that only form in the cores of stars hundreds of times the sun's mass. Spotting one would be like finding a fossilized footprint from a mythical beast, proving those cosmic titans truly existed. Every galaxy JWST examines is a time capsule, preserving the conditions of an era lost to the ages. With each new observation, it stitches together a clearer picture of how the first stars lived, died, and set the universe on the path to complexity. They may be gone, but their legacy shines through in every atom, every galaxy, and every beam of light that reaches us across the gulf of time. Spotting the first stars is like trying to photograph a candle flame from across an ocean, not just because of the staggering distance, but because the universe itself has stretched their light beyond recognition. These population 3 stars existed during the cosmic dark ages, a time so remote that their photons have been redshifted into near oblivion, their wavelengths stretched by the expansion of space from visible ultraviolet into faint infrared whispers. The most advanced telescopes today are effectively blind to their original light, forcing astronomers to become cosmic detectives, piecing together clues from secondary evidence instead of direct observation. The challenge starts with their sheer distance. Light from those ancient stars has traveled over 13 billion years to reach us, but the universe hasn't stayed still in that time. Space itself has expanded, stretching the wavelengths of that light so dramatically that what once shone as visible or ultraviolet radiation now arrives as far infrared, a part of the spectrum drowned out by interstellar dust and the glow of younger stars. Even the James Webb Space Telescope, designed to peer into this era, can't see individual population 3 stars directly. Their luminosity, though immense by human standards, is simply too diluted across cosmic time. But distance isn't the only hurdle. The first stars lived fast and died young, leaving no living relics to study. Unlike later stellar generations that still twinkle in our night sky, these pioneers burned out within a few million years, vanishing before the first galaxies fully formed. Their brief existence means the odds of catching one midlife are astronomically low, like hoping to snap a photo of a mayfly during its single day of life. What we're left with are the echoes of their deaths, the chemical residues they scattered in supernova, the ionization bubbles they carved in primordial gas, and the gravitational waves their collapses may have rippled across spacetime. Then there's the contamination problem. The universe today is cluttered with newer stars, galaxies, and nebulae that outshine any faint traces of the first light. Isolating population 3 signatures is like listening for a single voice in a roaring stadium. Even when we find extremely metal-poor stars, ancient survivors from nearly as early, they still contain traces of heavier elements, proving they formed from gas already polluted by that first generation. True population 3 stars would be chemically pure, a fingerprint we've yet to definitively spot. Yet hope isn't lost. Innovative techniques are pushing the boundaries of detection. Some teams search for the shadowy absorption lines left when population 3 starlight passed through primordial gas clouds, a ghostly imprint preserved in quasar spectra. Others model the subtle temperature fluctuations their supernova would have caused in the cosmic microwave background. There's even speculation that their remnants, those first black holes, might reveal themselves through lensing effects or gravitational wave signals. The irony is profound. The stars that literally lit up the universe now hide in its deepest shadows, their legacy written everywhere except in direct light. But every constraint they impose only sharpens the hunt. If we do someday capture their faint afterglow, it won't just be a discovery, it'll be a window into the universe's first dawn, a glimpse of the moment darkness gave way to light. Until then, their elusiveness reminds us that some cosmic truths demand more than observation. They require imagination, patience, and a willingness to piece together the universe's oldest story, one fragile clue at a time. Were the first stars solitary titans ruling empty cosmic landscapes, or did they emerge in glittering sibling clusters, their fates intertwined from birth? This debate isn't just academic, it reshapes our understanding of how starlight first pierced the darkness. On one side, simulations suggest many early stars formed alone, their colossal size a consequence of pristine gas clouds collapsing into singular, monolithic cores. Without heavy elements to help fragment the gas, these clouds lack the ability to splinter into smaller stars, leaving gravity to craft single, unstable behemoths. Picture a cosmic sculptor shaping a mountain from marble with no tools to carve finer details. The result is unavoidably massive. Yet other models paint a more communal picture. Turbulence in primordial gas clouds could have created dense knots, each collapsing into its own protostar before gravity fully consolidated them. Imagine a pot of boiling water where bubbles form and merge unpredictably. Some regions might have birthed tight groups of stars, their gravitational dances pulling them into orbits around one another. These clusters wouldn't have resembled modern ones like the Pleiades, though. Instead, they'd be raw and chaotic, with stars dozens of times the Sun's mass jostling for dominance in a celestial free-for-all. The distinction matters because a star's environment shapes its destiny. Isolated giants would have lived and died without interference, their supernova scattering metals across vast, untouched regions. But stars in clusters could have influenced each other's evolution dramatically. Radiation from a massive neighbor might strip away a sibling's outer layers, altering its lifespan. Collisions, rare but cataclysmic, could merge stars into even larger monsters, triggering hypernova that seeded the cosmos with rarer elements. And when one star exploded, its shockwaves might compress nearby gas, sparking new rounds of star formation like a chain reaction. Evidence hides in the chemical fingerprints of ancient stars, ultra-metal, poor stars in our galaxy's halo, some nearly as old as the universe itself, show unexpected variations in element ratios. These anomalies could hint at pollution from multiple supernovae in a clustered environment where ejecta mixed unevenly. Alternatively, they might reflect the isolated explosions of solitary giants. The James Webb Space Telescope could tip the scales, spotting distant galaxies where young stars are grouped in ways that mirror or defy these early conditions. What's fascinating is how this debate echoes across cosmic time. Modern star-forming regions like Orion show both scenarios, lone massive stars and dense clusters. If the first stars leaned toward isolation, it suggests the early universe was a quieter place, with light emerging in sporadic bursts. But if they clustered, their collective radiance might have reionized the cosmos faster, accelerating the universe's transition from darkness to light. Either way, their choices, loners or siblings, set the stage for everything that followed, from galaxy formation to the chemistry of life itself. The radiation from the first stars didn't just illuminate the cosmos, it rewrote the rules of star formation entirely. These primordial powerhouses blasted their surroundings with ultraviolet light so intense it could strip electrons from atoms light years away, creating vast bubbles of ionized gas that expanded like cosmic shockwaves. Within these bubbles, the conditions for new star formation vanished. Gas became too hot and energetic to collapse under gravity's pull. It was as if the universe's first architects had flipped a master switch, temporarily suppressing stellar birth across entire regions. Yet paradoxically, just beyond these blistering spheres of influence, their radiation set in motion events that would trigger the next wave of celestial creation. Here's how the cycle worked. When ultraviolet light hit surrounding neutral hydrogen, it didn't just ionize atoms, it also heated the gas, increasing its pressure. This created expanding shells of dense material at the edges of ionization fronts, like snow piling up ahead of a plow. Over millions of years, these compressed layers grew massive enough to overcome thermal pressure and collapse under their own weight. The result, new generations of stars forming in pristine molecular clouds that might have otherwise remained dormant. Some simulations show these shock-induced second-generation stars forming in elegant rings around the voids carved by their predecessors, a celestial echo of the original giant's influence. The stellar winds pouring from these early stars added another layer of complexity. Unlike modern stars that lose mass gradually, population 3 stars ejected material at ferocious speeds, up to 1,000 kilometers per second, creating turbulent cavities in the interstellar medium. These winds acted like cosmic sculptors, carving intricate channels through nearby gas clouds and triggering cascading collapses in their wake. In some regions, they shredded potential star-forming clouds before they could coalesce. In others, the collision of multiple wind bubbles created regions of extraordinary density where star formation erupted like fireworks. Perhaps most remarkably, the deaths of these stars created feedback loops that spanned generations. When the first supernova exploded, their blast waves enriched the surrounding gas with heavy elements while simultaneously heating it to extreme temperatures. Initially, this suppressed further star formation, but as the ejected material cooled over millions of years, those same heavy elements acted as cosmic refrigerants, allowing gas to shed heat more efficiently. This cooling enabled more numerous smaller stars to form in subsequent cycles, gradually transitioning the universe from an era of isolated giants to one filled with the diverse stellar populations we see today. The legacy of these feedback mechanisms is written across the cosmos. Modern galaxies still bear the imprint of those early cycles in their metallicity gradients, the way heavier elements decrease in concentration toward galactic outskirts, mirroring where primordial feedback was weakest. Even the distribution of globular clusters, ancient relics of vigorous star formation, may trace back to where shock waves from the first supernova triggered secondary bursts of creation. Feedback wasn't just a side effect of the first stars, it was the universe's way of self-regulating its evolution, balancing destruction and creation in a dance that continues to shape galaxies 13 billion years later. Not all the first stars ended their lives in brilliant supernova. Some may have vanished without a trace, collapsing silently into black holes that would shape the universe in ways we're only beginning to understand. These primordial black holes, born from the deaths of the most massive population, 3 stars, could have been the universe's first dark architects, their gravity sculpting galaxies long before light could pierce the cosmic fog. Imagine a star so immense that its core couldn't even explode. When its fuel ran out, gravity won without resistance. The entire star would implode, swallowing itself whole and leaving behind a gravitational pit so deep not even light could escape. Unlike modern black holes, which form from stars enriched with heavier elements, these ancient ones emerged from pure hydrogen and helium, making their collapse faster and more efficient. Some theories suggest they could have been hundreds or even thousands of times more massive than the Sun, far larger than most black holes forming today. But here's where it gets fascinating. These black holes didn't just lurk in the darkness, they may have become the seeds of the first galaxies. As they drifted through clouds of primordial gas, their immense gravity pulled in surrounding material, creating swirling disks of superheated plasma. Friction within these disks would have generated intense radiation, heating nearby gas and preventing it from collapsing into new stars too quickly. In doing so, they could have regulated the growth of early galaxies, slowing star formation just enough to allow structures to stabilize rather than burning out in a frenzied burst. Some astronomers speculate that these black holes didn't just influence galaxies, they might have become their cores. Over time, gas and smaller black holes could have merged around them, forming the supermassive black holes we now find at the centers of nearly every large galaxy, including our own Milky Way. If true, that means the dark hearts of modern galaxies could be direct descendants of the first stars, their origins lost in the earliest moments of time. Yet the evidence remains elusive. Primordial black holes would be nearly impossible to detect directly. They emit no light, and their small size makes gravitational lensing unlikely. Instead, researchers look for indirect clues like distortions in the cosmic microwave background or unexplained ripples in spacetime from ancient mergers. Some theories even suggest these black holes could account for part of the universe's missing dark matter, their invisible mass weaving through galaxies like ghosts. The implications are staggering. If these black holes existed in abundance, they could have jump-started cosmic structure far earlier than previously thought, turning the universe from a formless void into a web of galaxies in what would have felt like an instant. Their gravity might have redirected streams of gas, creating the filaments along which galaxies later aligned. And their violent mergers could have been the first sources of gravitational waves, ripples in spacetime that we've only just begun to detect. Whether they're confirmed or remain theoretical, primordial black holes force us to reconsider the universe's infancy. The first stars didn't just bring light, they might have planted darkness at the heart of everything, a hidden force guiding the cosmos toward the structured beauty we see today. Their story isn't written in starlight, but in the silent pull of gravity, the unseen framework of existence itself. The first stars didn't just light up the cosmos, they built the scaffolding for everything that came after. Their radiance and explosive deaths didn't merely enrich the universe with heavy elements, they triggered the gravitational domino effect that assembled the first galaxies. Picture a cosmic construction site where colossal stars acted like foremen, their supernova blasting shock waves through surrounding gas, compressing it into dense pockets ripe for collapse. These weren't the grand spirals we see today, but tiny, misshapen dwarfs, galaxies so faint and small they'd barely register next to a single star in our modern night sky. Yet their modest appearance belied their significance. These primordial dwarfs were the universe's first experiments in large-scale structure, the prototypes for every galaxy that followed. Gravity was the invisible architect, weaving stars together into loose clusters within halos of dark matter. Simulations reveal a chaotic process. Gas clouds polluted by the ashes of the first supernova cooled faster, fragmenting into smaller stars that could orbit one another without being torn apart by gravitational tides. Over eons, these stellar clumps merged, their dark matter halos swallowing smaller neighbors in a relentless dance of accretion. The result, proto-galaxies barely 1% the mass of the Milky Way, glowing feebly with the light of their few million stars. Unlike modern galaxies, which rotate in elegant disks, these early dwarfs were turbulent and disorganized, their stars moving in erratic orbits like swarms of fireflies caught in a storm. What's astonishing is how quickly this happened. Within a few 100 million years of the first starlight, the universe transformed from a formless void into a tapestry of dwarf galaxies, each a crucible for further star formation. Ultraviolet radiation from their young stars ionized nearby gas, while supernova blew bubbles that both suppressed and triggered new rounds of star birth. This feedback loop, creation and destruction intertwined, allowed galaxies to grow in fits and starts, balancing their own growth against the violence of their stellar inhabitants. Some of these ancient dwarfs still exist today, orbiting our Milky Way like living fossils. Galaxies like Segway 1 or Draco, barely visible even through telescopes, contain stars with almost no heavy elements, a telltale sign they formed from nearly pristine gas. Studying them is like cracking open a time capsule. Their dim glow carries the chemical fingerprints of the first supernova, offering clues about how the earliest stellar generations shaped their environments. But the real turning point came when these dwarfs began to collide. Gravity pulled them into clusters where they merged over billions of years, forming larger and larger structures. Every massive galaxy we see today, from stately spirals to glowing ellipticals, owes its existence to those primordial building blocks. The stars within them, forged in the hearts of the first dwarfs, became the raw materials for everything that followed: planets, nebulae, and ultimately, the chemistry of life itself. This is the hidden legacy of the first stars. They didn't just shine, they built. Their light was the spark, but their true gift was the gravitational blueprint they left behind, a recipe for turning darkness into structure, chaos into cosmos. Every galaxy, every star, every atom in our bodies traces back to those fragile beginnings, when the universe first learned how to assemble itself from the ashes of its earliest flames. Pinpointing the exact moment when starlight first pierced the cosmic dark isn't just a matter of curiosity, it's a detective story written in the faintest whispers of the universe itself. Current estimates place the birth of the first stars somewhere between 200 and 400 million years after the Big Bang, a window so narrow in cosmic terms it's like identifying the exact minute a single raindrop fell in a prehistoric storm. But how do we trace something so ancient when no direct evidence remains? The clues lie in three brilliant lines of investigation. the cosmic microwave background, the shadows of primordial gas clouds, and the chemical fingerprints of the universe's oldest surviving stars. Take the cosmic microwave background first, the afterglow of the Big Bang itself. This faint microwave static, detectable in every direction of space, carries subtle imprints of the universe's teenage years. When the first stars ignited, their ultraviolet radiation began ionizing the surrounding hydrogen, creating bubbles of charged particles that left distinct polarization patterns in the CMB. Satellite missions like Planck have mapped these patterns with exquisite precision, revealing that reionization, the universe's great awakening, was well underway by 500 million years after the Big Bang. Since stars must have existed long enough before that to build up sufficient radiation, scientists trace the timeline backward, placing their emergence comfortably in that 200 to 400 million year window. Then there's the forensic evidence hidden in quasars, the brilliant beacons powered by supermassive black holes in the early universe. As their light travels through space, it passes through ancient gas clouds that absorb specific wavelengths, leaving dark lines in the spectrum like barcodes. Some of these clouds are so pristine they contain almost no heavy elements, suggesting they formed before stars had time to pollute the cosmos. Others show faint traces of carbon and oxygen, the chemical footprints of the first supernova. By measuring the ratios of these elements and comparing them to theoretical models, astronomers can estimate how long stars had been burning before enriching those clouds. The answer, roughly 200 million years of star formation before the pollution became detectable. Perhaps the most compelling clues come from the Milky Way's oldest stellar inhabitants. Stars like SMSS J031300, 36,670,839, 3, found in our galaxy's halo, contain so few heavy elements they're almost pure hydrogen and helium relics from an era just one generation removed from the first stars. Their chemical makeup acts like a time capsule, preserving the conditions of the gas clouds they formed from. By dating these ancient stars using radioactive isotopes like uranium and thorium, scientists can work backward to estimate when their predecessors must have lived. The results consistently point to a cosmic dawn no later than 400 million years post-Big Bang. But here's the twist: the timeline isn't uniform across the universe. Some regions where dark matter was denser likely formed stars tens of millions of years earlier than others. Imagine the first starlight not as a sunrise but as a slow wave of flickering campfires igniting one by one across a vast landscape. The James Webb Space Telescope has spotted galaxies like Glass Z13, whose light dates back to just 300 million years after the Big Bang, already massive and evolved, hinting that their stars must have begun forming even earlier. Meanwhile, simulations suggest the very first protostars could have flickered to life as early as 100 million years in exceptionally dense pockets of the cosmos. The beauty of this detective work lies in its convergence, like triangulating a signal from multiple antennas. Each line of evidence, CMB polarization, quasar absorption lines, ancient stellar chemistry, narrows the window further. Together, they paint a picture of a universe that spent its first 100 million years in darkness, then slowly, tentatively began to glow. By 400 million years, the fire was well and truly lit, setting the stage for the explosive star formation that would follow. It's a timeline measured not in rocks or fossils, but in the resonant echoes of light and shadow, a story written in the very fabric of space itself. The fiery deaths of the first stars didn't just mark the end of an era, they set the stage for life itself. When those primordial giants exploded as supernovae, they became cosmic alchemists, transforming the universe's sparse hydrogen and helium into something revolutionary: carbon, oxygen, nitrogen, and other elements essential for planets and biology. This wasn't just a minor chemical upgrade, it was the universe's first step toward complexity, turning a sterile void into a potential cradle for life. Think of a supernova as the ultimate pressure cooker. In the final moments of a massive star's life, its core becomes a nuclear forge where temperatures and pressures reach extremes impossible anywhere else. Hydrogen had fused into helium during the star's lifetime, but now, under crushing gravity, helium atoms smashed together to form carbon, the backbone of all organic chemistry. Oxygen followed as carbon nuclei captured additional helium, while nitrogen emerged from collisions between carbon and hydrogen. These weren't trace byproducts. Supernova ejected them in staggering quantities, scattering them across light years like seeds in cosmic winds. The numbers are humbling. A single population 3 supernova could spew out enough oxygen to form thousands of Earth-sized planets, along with carbon equivalent to millions of Mount Everest-sized diamonds. But raw abundance wasn't the miracle, it was how these elements behaved. Carbon's unique ability to form long, stable chains allowed it to become the scaffold for complex molecules. Oxygen's reactivity made it the universal chemical fuel, while nitrogen's stability let it anchor essential compounds like amino acids. Without these traits, chemistry would have stalled at simplicity, leaving the universe forever barren. Yet creation wasn't instant. Early supernovae from the most massive stars operated differently than later ones. Their explosions were so violent they likely produced unusual isotopes like calcium-60 and titanium-44, which don't exist in modern supernova remnants. Some models suggest they even forged gold and platinum in seconds through rapid neutron capture, a process requiring energy so extreme they're rarely replicated today. These exotic reactions mean the first stellar deaths didn't just enrich the cosmos, they seasoned it with elements modern stars can't easily reproduce. The journey from scattered stardust to life's building blocks wasn't straightforward, though. For millions of years, these heavy elements drifted through space, gradually mixing with fresh hydrogen in molecular clouds. Turbulence and gravity worked in tandem, kneading them into denser pockets where new stars formed, stars like our Sun, born from gas already laced with carbon and oxygen. This second-generation's planetary systems inherited the chemistry of those ancient explosions, with rocky worlds forming from silicon and iron, while carbon-rich molecules gathered in icy comets and asteroids. Here's where the story turns personal. Every atom in your body heavier than helium, the calcium in your bones, the iron in your blood, the phosphorus in your DNA, was forged in the heart of a dying star. The oxygen you breathe likely originated in a supernova that detonated billions of years before Earth existed. Even the silicon in your smartphone traces back to those cataclysmic explosions. We're not just observers of cosmic history, we're literal stardust, the universe's way of taking its first elemental ingredients and arranging them into something capable of understanding its own origins. The final twist: these processes weren't guaranteed. Had the first stars been slightly less massive, they might not have reached the temperatures needed to create carbon. Slightly more massive, and their supernova could have vaporized nearby gas clouds instead of enriching them. The balance was exquisite, a cosmic tightrope walk where the conditions for life's chemistry hinged on stellar deaths happening precisely the right way. Every breath you take is a testament to that improbable perfection, a reminder that the universe didn't just create life, it earned it. Could the first stars have been fueled by something even stranger than hydrogen? A radical idea suggests that dark matter, not gas, might have powered the universe's earliest light. These hypothetical dark stars would have been unlike anything in the modern cosmos, glowing not from nuclear fusion but from the annihilation of dark matter particles colliding in their cores. Picture a star that burns with eerie, persistent light for millions of years, its energy drawn from the invisible sea of matter that still permeates the universe today. Instead of collapsing until fusion ignites, these dark stars would have grown to staggering sizes, potentially reaching millions of times the mass of our Sun, so large they'd make even the largest population 3 stars look like specks in comparison. The physics behind dark stars hinges on a peculiar property of certain theoretical dark matter particles called WIMP, weakly interacting massive particles. If these particles can annihilate upon contact, releasing energy, then dense clumps of dark matter in the early universe could have formed gravitational traps for hydrogen gas. As the gas gathered, dark matter annihilations at the core would heat it enough to prevent collapse, creating a stable, glowing object powered by an entirely different mechanism. These stars wouldn't flicker like normal ones. They'd emit a steady, diffuse light, potentially in the infrared spectrum, with surface temperatures cooler than modern stars but far greater size. Not all researchers are convinced, though. Critics point out that dark stars require very specific dark matter properties, particles that annihilate efficiently, but not so violently they'd prevent star formation altogether. Plus, there's no direct evidence they ever existed, yet tantalizing clues linger. Some models suggest dark stars could explain anomalies in the cosmic infrared background, an unexplained glow that telescopes like Spitzer and JWST have detected. If dark stars were common, their prolonged lifespans might also account for why reionization happened more gradually in some regions than others. Meanwhile, other theorists propose an even wilder scenario, that the first stars formed in a fraction of the time we've assumed. Traditional models suggest it took hundreds of millions of years for gravity to pull together the first gas clouds, but alternative simulations show that under certain conditions, like unusually dense dark matter halos or cosmic turbulence from early black holes, protostars could have ignited in as little as tens of millions of years. This fast-track star formation would mean the cosmic dark ages ended abruptly, with starlight erupting across the universe like a sudden thunderstorm after a drought. Evidence for this might lie in the universe's most distant galaxies. JWST has spotted surprisingly mature galaxies existing shockingly early, their stars already old by the time the universe was a few 100 million years old. If confirmed, these observations could force a rewrite of the standard timeline, implying star formation wasn't just faster but perhaps more efficient in the pristine environment of the early cosmos. Gas clouds back then lacked dust and heavier elements, which ironically might have made them collapse more easily, like a soufflé rising perfectly in an oven without impurities to disrupt its structure. The debate isn't just academic, it reshapes how we search for the universe's origins. If dark stars existed, their remnants could be hiding in plain sight as unusually massive black holes or exotic stellar relics. Faster star formation, meanwhile, would imply that galaxies assembled their first stars in frantic bursts rather than steady accumulation, changing how we interpret the chemical signatures of ancient stars. Both ideas challenge the neat narrative of cosmic dawn, reminding us that the early universe was a laboratory for physics we're still struggling to understand. What's fascinating is how these theories, however speculative, force us to reconsider the tools we use to probe the past. Dark stars would emit light invisible to telescopes tuned for fusion-powered stars, while rapid star formation might leave clues in the distribution of the oldest globular clusters. The answers could be hidden in data we've already collected, waiting for the right perspective to reveal them. Until then, these alternate visions of the first stars stand as bold reminders that the universe's beginnings might be stranger and more wonderful than we've dared to imagine. Buried in the outskirts of our Milky Way, ancient stars flicker like cosmic time capsules, their light carrying secrets from an era long before Earth existed. These stellar relics, known as ultra-metal poor stars, contain barely a trace of elements heavier than hydrogen and helium chemical fossils, pointing back to a time when the universe had only just begun forging atoms beyond lithium. Studying them is like cracking open a geological layer from the dawn of time, except instead of rock strata, we're reading layers of elemental abundance etched into starlight. Take the star SMSS J160540, 1844323, one discovered in the Milky Way's halo. Its iron content is roughly 1.5 million times lower than the Sun's, so scarce you'd need a cosmic microscope to find it. Yet this poverty is precisely what makes it precious. Stars like this likely formed from gas clouds polluted by just one or two previous supernovae, preserving pristine snapshots of the first stellar generation's explosive deaths. Their atmospheres act like cosmic chemistry sets, revealing which elements those early stars produced, how violently they exploded, and even how much material they flung into the void. The detective work hinges on spectroscopy, splitting starlight into rainbows that unveil missing wavelengths, each gap corresponding to elements absorbed by the star's outer layers. When astronomers analyze these fingerprints, they uncover bizarre patterns. Some metal-poor stars show unexpected spikes of carbon relative to iron, hinting that their progenitor stars might have died in unusual, faint supernovae that ejected outer layers rich in carbon but left heavier elements trapped in collapsing cores. Others reveal puzzling overabundances of strontium or barium, elements typically forged in later generation stars, suggesting the first supernova might have produced them through rare, high-energy reactions we no longer see today. One of the most revealing cases is He 1327, 2326, a star so metal-deficient its composition mirrors theoretical models of second-generation stars born from purely population Roman III debris. Its bizarrely high nitrogen levels defy modern stellar physics, unless its ancestors were massive enough to trigger unique fusion chains that don't occur in today's stars. Like an ancient scroll written in half-familiar script, these anomalies force us to rethink how the earliest stars lived and died. The very elements that seem out of place are the clues pointing to stellar behaviors we've never witnessed directly. But finding these relics isn't easy. They're needles in a galactic haystack hiding among billions of younger, metal-rich stars. Surveys like SkyMapper in Australia scan millions of stars, flagging candidates with unusual colors, often bluer than expected due to their lack of metal-induced absorption lines. Confirming them requires painstaking follow-up with high-resolution spectrographs on telescopes like the Very Large Telescope in Chile, where astronomers hunt for the faintest traces of heavier elements. What's astonishing isn't just what these stars reveal about the past, but how long they've endured. While their massive population Roman III ancestors burned out within millions of years, smaller second-generation stars like He 0107 5240, roughly 80% the Sun's mass, have been shining for over 13 billion years. They've witnessed the entire history of cosmic structure formation, from primordial gas clouds to the assembly of galaxies like our own. Their longevity means we're not just studying fossils, we're interviewing survivors. Yet the real treasure lies in their diversity. No two ultra-metal-poor stars show exactly the same chemical pattern, implying their progenitors weren't uniform either. Some suggest the first stars varied wildly in mass, from 30 solar masses to over 300, each leaving distinct elemental signatures in their wake. Others hint at exotic supernova powered by antimatter or magnetic fields, events so extreme they've never been observed in the modern universe. Every outlier challenges our assumptions, painting a picture of cosmic dawn far more chaotic and inventive than we'd imagined. This is stellar archaeology at its most profound, reading the universe's earliest chapters not in ancient light that's traveled billions of years, but in the enduring glow of stars that have carried those stories within them all along. They're living bridges to an unreachable past, their atoms whispering secrets from an era when the cosmos was still learning how to build the ingredients of everything we know. The cosmic microwave background isn't just a relic of the Big Bang. It's a palimpsest, a canvas where the universe's earliest chapters were written and then subtly overwritten by the first starlight. This faint afterglow, now cooled to mere whispers of microwaves, carries distortions so delicate they're like fingerprints pressed into cosmic history. Among these marks lies evidence of reionization, the moment when ultraviolet light from the first stars tore through the cosmic fog, stripping electrons from hydrogen atoms and leaving an imprint that's lasted nearly 13 billion years. What makes these distortions so revealing is their scale. When the CMB was born, the universe was a plasma so hot and dense that light couldn't travel far before scattering. After recombination, when atoms formed and the cosmos became transparent, photons streamed freely, creating the smooth microwave glow we detect today. But when the first stars ignited, their intense radiation reionized vast swaths of hydrogen, introducing free electrons back into the cosmos. These electrons scattered CMB photons once more, subtly altering their polarization patterns in a way that depends on exactly when and how quickly reionization occurred. The telltale sign is called E-mode polarization, a specific swirl pattern in the CMB's light that acts like a cosmic timestamp. Planck satellite data reveals that this polarization wasn't uniform. Some regions show stronger signals, suggesting patches of the universe ionized earlier than others. This patchiness aligns perfectly with the idea that the first stars didn't light up all at once, but flickered to life in clusters, their radiation bubbles merging over time like ink spreading through water. The CMB's polarization maps even hint at how massive those early stars were. Sharper ionization edges would point to fewer, more luminous sources, while fuzzier boundaries suggest numerous smaller stars. But the real breakthrough came when scientists noticed a peculiar discrepancy. The optical depth of the CMB, a measure of how much its photons scattered during reionization, suggests this process was well underway by the time the universe was 500 million years old. Yet the timing is tighter than expected. If the first stars formed around 200 million years after the Big Bang, their cumulative radiation should have taken longer to ionize the cosmos. This mismatch implies something startling. Those early stars might have been even more efficient at producing ultraviolet photons than models predict, or perhaps additional sources like early quasars contributed to reionization's rapid pace. The CMB also harbors clues about the environment these stars inhabited. Tiny temperature fluctuations in the background radiation correspond to regions where matter was slightly denser in the early universe, seeds for future galaxies. By cross-referencing these density variations with polarization patterns, astronomers can reconstruct how the first stellar nurseries were distributed. Some models suggest they clustered along dark matter filaments like beads on a string, their radiation traveling along these cosmic highways to ionize vast volumes. What's remarkable is how these observations intertwine with other lines of evidence. Quasar absorption spectra show pockets of neutral hydrogen lingering even as late as 1 billion years after the Big Bang, implying reionization was a messy, drawn-out process. Meanwhile, JWST glimpses of early galaxies reveal objects far brighter than predicted, potentially upending assumptions about how quickly stars assembled. The CMB ties these threads together, offering a broad strokes timeline while leaving room for localized chaos. Yet the most tantalizing possibility lies ahead. Future observatories like the Simons Observatory or CMB-S4 aim to detect primordial gravitational waves, ripples in spacetime from the universe's inflationary phase, by studying B-mode polarization, a subtler signal than E-modes. If successful, they could uncover whether the first star's formation was influenced by even earlier cosmic events, linking the birth of light to the violent tremors of the Big Bang itself. The CMB isn't just a snapshot, it's a living record still revealing secrets about how darkness first gave way to dawn. The hunt for the universe's first starlight is about to enter a new era, armed with telescopes so advanced they could finally turn speculation into observation. Leading the charge is NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s with a singular mission: to peer deeper into cosmic dawn than any instrument before. Unlike Hubble or even JWST, Roman's wide-field infrared vision is designed to survey vast swaths of the sky with unprecedented sensitivity, scanning for the faintest whispers of population 3 stars' aftermath. Its secret weapon, a staggeringly large field of view 100 times wider than Hubble's, allowing it to capture the rarity of these ancient stellar ghosts amid the cosmic noise. But Roman won't be working alone. The European Extremely Large Telescope, or ELT, currently under construction in Chile's Atacama Desert, will complement these efforts with its 39-meter primary mirror, the largest ever built for optical and infrared astronomy. Imagine the resolving power to pick out individual stars in galaxies so distant their light has traveled over 13 billion years. The ELT's mirrors could detect the chemical signatures of second-generation stars still bearing traces of their population 3 ancestors, like finding faded ink on a parchment nearly erased by time. Together, these instruments form a tag-team approach. Roman scans the cosmic haystack while ELT zeroes in on the needles. The real game-changer lies in spectroscopy. Roman's prism-like instruments will dissect the light from primordial galaxies with precision, hunting for telltale gaps in the spectrum where hydrogen absorbed specific wavelengths. A complete absence of certain heavy elements in these absorption lines would signal galaxies illuminated solely by population 3 starlight, like spotting a candle's glow in a room no one's entered for billions of years. Meanwhile, the ELT's high-resolution spectrographs could detect anomalies in ancient starlight, such as unusual ratios of helium to hydrogen, hinting at pollution from supernova unlike any seen today. Yet the most tantalizing possibility involves gravitational lensing. Roman will exploit Einstein's prediction that massive galaxy clusters can bend light like a magnifying glass, amplifying the glow of objects behind them. A perfectly aligned cluster might magnify a distant population Roman 3 star's direct light, normally far too dim to detect, into visibility for a fleeting moment. These cosmic mirages could offer our only chance to glimpse an individual first-generation star before it vanishes forever into the infrared background. But the surprises don't stop there. Proposed missions like LUVOIR or the Habitable Worlds Observatory aim to push boundaries even further, with mirrors larger than JWST and ultraviolet capabilities to study reionization's earliest stages. And on the ground, the Square Kilometre Array Radio Telescope will map hydrogen's distribution during the cosmic dark ages, tracing where the first star's radiation sculpted bubbles of ionization in the primordial fog. What makes this next decade revolutionary isn't just better technology, it's the convergence of multiple lines of evidence. Roman's wide surveys might identify candidate regions, ELT's spectroscopy could confirm their chemistry, and radio telescopes like SKA might pinpoint the exact epochs when starlight first pierced the dark. Each instrument fills a piece of the puzzle, and together they could reconstruct a chapter of cosmic history we've only ever imagined. The dream isn't just to prove population 3 stars existed, it's to understand their rhythms, their deaths, and the echoes they left in the void. After all, these weren't just stars, they were the matchsticks that lit the universe, and soon we might finally see their glow. The first stars didn't just illuminate the cosmos, they poisoned it in the most beautiful way possible. When those primordial giants exploded, they didn't merely sprinkle heavy elements into their immediate surroundings. They blasted them clear across intergalactic space, turning pristine voids into chemical reservoirs that would shape galaxies for billions of years. Picture a supernova shockwave rippling through the universe like a stone thrown into a pond, carrying carbon, oxygen, and iron far beyond its birthplace. These metals' cosmic pollution on the grandest scale became the raw ingredients for everything that followed, from swirling galactic disks to the DNA in your cells. This wasn't a gentle dispersal. The most massive population 3 stars died in hypernova, explosions so violent they could launch material at nearly the speed of light. Their ejecta didn't just drift, they carved tunnels through the interstellar medium, propelled by jets of energy that punched through gas clouds like bullets through fog. Some models suggest these shockwaves traveled millions of light-years before slowing, seeding far-flung regions with elements that shouldn't have existed there yet. We see echoes of this in modern quasar spectra, where distant gas clouds billions of light-years away contain trace metals long before any nearby stars could have produced them. The universe's first pollution wasn't local, it was a pandemic of enrichment, spreading faster and farther than anyone once imagined. What's astonishing is how quickly this transformation unfolded. Within just a few 100 million years, supernova turned the cosmos from chemically sterile to richly complex. Early galaxies acted like inefficient factories, losing up to half their heavy elements to galactic winds, vast outflows powered by supernova explosions and radiation pressure. These winds carried metals into the circumgalactic medium, the sparse gas surrounding galaxies, where they mixed with pristine hydrogen and helium. Over time, this enriched material cooled and funneled back into galaxies, fueling new generations of stars with increasingly diverse chemistry. It was a cosmic recycling program on a scale so vast it's almost incomprehensible. The smoking gun lies in the universe's most isolated corners. Even the diffuse gas between galaxy clusters, known as the intergalactic medium, contains trace amounts of heavy elements, roughly 1% the abundance found in our Sun. This metallicity flaw proves that early supernova pollution was nearly universal, reaching regions where no stars have ever formed. Some of this material might have been carried by powerful quasar outflows, while other portions were likely transported by tidal streams during galaxy collisions. But the sheer uniformity suggests that the first star's explosions created a background haze of metals woven into the fabric of space itself, yet not all elements spread equally. Lighter ones like carbon and oxygen traveled farthest, their atoms riding shockwaves like leaves on the wind. Heavier elements like iron and gold tended to cluster near their birthplaces, trapped by their own inertia. This explains why ancient stars in the Milky Way's halo show such wild variations in element ratios, some rich in carbon but devoid of iron, others laced with odd R-process elements like europium. Each is a snapshot of different pollution events, some from solitary supernova, others from clustered explosions where ejecta mixed unevenly. It's as if the early universe was a chef experimenting with recipes, tossing random handfuls of ingredients into the cosmic soup. The real marvel is how this pollution paved the way for life. Without those first heavy elements, gas couldn't cool efficiently enough to form small, stable stars like our Sun. Planets would have been impossible: no silicon for rocks, no oxygen for water, no carbon for organic molecules. Even the dust grains that later shielded complex molecules in interstellar space were forged in those early explosions. The universe didn't just become chemically richer, it became capable of chemistry itself. Today, we're still mapping the fallout of this primordial pollution. Astronomers use ultraviolet telescopes to trace ionized metals in the intergalactic medium, while simulations recreate how supernova winds tunneled through the early cosmos. Each discovery reveals how chaos and order intertwined, how the violent deaths of the first stars created the conditions for galaxies, planets, and life to emerge. Their pollution wasn't destruction, it was the universe learning to build with more than just hydrogen and helium, turning simplicity into complexity one atom at a time. The universe doesn't make stars the way it used to. 13 billion years ago, star formation was a high-stakes gamble, violent, inefficient, and dominated by behemoths hundreds of times the Sun's mass. Today, it's a refined art, with smaller, stable stars forming in orderly nurseries like the Orion Nebula. The difference: chemistry. The first stars had nothing but hydrogen and helium to work with, while modern stars inherit a universe already seasoned with heavy elements from countless supernovae. Picture the early cosmos as a kitchen stocked with only salt and flour. When the first stars formed, they had no tools to control the chaos, no metals to help gas cool, no dust grains to radiate heat away. Gravity pulled entire gas clouds into singular, unstable clumps, like a baker trying to make one enormous loaf instead of dozens of rolls. These protostars grew unchecked, reaching masses so extreme their cores burned at staggering temperatures, fusing hydrogen into helium at rates that would make modern stars shudder. Their lives were short and spectacular, ending in supernovae that scattered the first heavier elements into the void. Fast forward to today, and star formation is a far more delicate process. Molecular clouds now contain traces of carbon, oxygen, and silicon, tiny impurities that act like cosmic refrigerants. As gas contracts, these elements emit infrared radiation, allowing heat to escape and the cloud to fragment into smaller, more stable pockets. It's like adding ice cubes to hot soup. The rapid cooling lets gravity build many smaller stars instead of a few unstable giants. The result, nurseries like the pillars of creation, where stars form in clusters with masses ranging from red dwarfs barely 1/10 the sun's size to occasional blue giants. The role of dust can't be overstated. In modern nebulae, microscopic silicate and graphite grains absorb starlight and re-emit it as heat, further cooling the gas. These dust particles also provide surfaces for hydrogen molecules to form, a critical step in star birth. The first stars had none of this: no dust to shield nascent protostars from radiation, no catalysts to help gas transition into molecular form. Their formation was a brute force process, while today's stars emerge from a finely tuned interplay of chemistry and physics. Even the environments differ radically. The first stars formed in near-total isolation, their colossal gravity drawing in gas from vast, pristine reservoirs. Modern stars, by contrast, compete for material in crowded nurseries, where magnetic fields and turbulence regulate their growth. Jets of plasma often erupt from young stellar objects, carving out cavities that limit how much mass they can accrete. It's a cosmic version of portion control, something the universe's first stars never had to worry about. Yet the most profound difference lies in longevity. Those early giants burned out in mere millions of years, while sun-like stars can shine for tens of billions. The universe traded raw power for stability, swapping short-lived titans for enduring embers capable of nurturing planets and, in at least one case, life. The Orion Nebula's stars won't reshape the cosmos like their ancestors did, but they'll burn long enough to give any orbiting worlds a chance to write their own stories. This shift wasn't just a matter of scale, it was a fundamental change in how the universe operates. The first stars were pioneers, forging the elements that would later enable smaller, more efficient stellar factories. Today's star-forming regions are the heirs to that legacy, turning the ashes of those early explosions into new possibilities. The recipe hasn't just been refined, it's been rewritten entirely, with every generation of stars adding new ingredients to the cosmic cookbook. Magnetic fields may seem like a modern cosmic phenomenon, something tied to spinning neutron stars or swirling galaxy cores, but their roots stretch back to the very first stars. In the primordial universe before starlight, these fields were little more than faint whispers, quantum fluctuations amplified by the churning of ionized gas. Yet even at these infinitesimal strengths, they could have played a surprising role in how the first stars formed, acting like invisible puppet strings guiding the collapse of those early hydrogen clouds. The key lies in turbulence. As gravity pulled gas together, it didn't move in smooth, orderly flows. Instead, it spiraled and fractured, creating chaotic eddies that could either accelerate or hinder star formation. Magnetic fields, however weak, introduced a subtle order to this chaos. Picture a pot of boiling water with strands of honey. Drizzled in the honey wouldn't stop the boiling, but it would create delicate threads of structure within the turmoil. Similarly, primordial magnetic fields could have channeled gas flows along invisible lines, preventing random motions from dispersing critical density peaks. Some simulations suggest this might have reduced fragmentation, helping gas collapse into fewer, more massive stars rather than scattering into useless turbulence. But magnetism's influence didn't stop there. Even fields a billion times weaker than Earth's could have resisted compression as gas clouds contracted, creating a form of cosmic stiffness that slowed star formation just enough to let protostars grow larger. Modern molecular clouds rely on magnetic fields to regulate their collapse. Why wouldn't the first stars have done the same, albeit on a more rudimentary scale? The difference was the lack of cosmic pollution. Without dust grains or heavy elements to help dissipate magnetic energy, early fields might have persisted longer, creating bizarre environments where magnetism competed with gravity in ways we never see today. The real wild card is amplification. As gas spun faster during collapse, even feeble magnetic fields could have been twisted and stretched like taffy pulled into tighter coils. This dynamo effect might have locally intensified fields to strengths capable of launching jets, narrow streams of plasma that shoot out from forming stars. We see these jets in modern star nurseries where they carry away excess angular momentum, allowing the star to keep growing. If the first stars produced similar jets, they'd have been monstrous, wider, faster, and more energetic than anything since. These outflows could have carved vast cavities in surrounding gas, shutting off star formation nearby or even triggering it elsewhere through shock waves. Evidence for this remains elusive, but tantalizing clues exist. The cosmic microwave background shows faint polarization patterns that might encode the imprint of primordial magnetic fields. Meanwhile, some ancient quasars exhibit strange Faraday rotation, a twisting of light's polarization that hints at magnetic fields permeating the early universe. If confirmed, these could be the fossilized signatures of magnetism's hand in shaping the first starlight. What's fascinating is how this reshapes our view of cosmic dawn. The first stars weren't just products of gravity and gas. They were born in a universe already humming with invisible forces, where even the weakest magnetic whisper could tilt the scales between a starless void and a sky ablaze with light. Their formation wasn't just a matter of mass and temperature, but of delicate balances we're only beginning to understand, a reminder that the universe's first light was never truly simple. Among the first stars, the most massive ones met a fate so violent it defies modern cosmic standards: pair instability supernova. These weren't ordinary stellar deaths where a core collapses into a neutron star or black hole. Instead, stars between 150 and 250 times the Sun's mass faced a runaway thermonuclear detonation that annihilated them completely, leaving no remnant behind. The physics behind this catastrophe begins deep in the star's core, where temperatures soar above 1 billion degrees. At such extremes, gamma-ray photons, normally harmless, become so energetic they spontaneously transform into pairs of electrons and positrons in a process called pair production. This switch from radiation to matter steals the star's internal pressure, like yanking the supports from a collapsing bridge. Gravity seizes the advantage. Without sufficient outward pressure, the core implodes violently, but here's the twist: this collapse isn't the end. The sudden compression heats the star's helium and oxygen layers to critical thresholds, triggering runaway fusion that rips through the star like a chain reaction in a nuclear bomb. The entire star detonates, releasing energy equivalent to 100 normal supernovae. For weeks, it outshines its host galaxy, blasting its outer layers into space at 10% the speed of light. Unlike modern supernovae that leave behind neutron stars or black holes, pair instability events scatter every ounce of the star's material into the cosmos, enriching the universe with staggering amounts of carbon, oxygen, and silicon. The aftermath resembles no other stellar explosion. Typical supernovae produce a mix of heavy elements, but pair instability events forge vast quantities of intermediate weight elements like titanium and nickel, up to 50 solar masses worth. These explosions were likely the primary source of the universe's first iron, seeding galaxies with materials essential for rocky planets. Yet their most distinctive signature is what they don't leave behind. No pulsar, no accretion disk, not even a gravitational whisper. Just an expanding shell of glowing debris fading into the void. Detecting these ancient cataclysms remains a challenge, but astronomers hunt for their chemical fingerprints in the universe's oldest stars. Metal-poor stars like SMSS J200,322, 54,114,203, found in the Milky Way's halo, show bizarrely high ratios of zinc to iron, a smoking gun for pair instability nucleosynthesis. Other candidates exhibit excesses of odd-numbered elements like phosphorus, which form more readily in these ultra-hot, symmetric explosions. Each discovery is a time capsule, preserving the elemental legacy of stars too massive to exist in today's universe. The cosmic impact of these explosions can't be overstated. Their sheer energy reionized vast regions of the early universe, while their heavy elements provided the universe's first fertilizer, enabling later stars to form smaller, cooler, and longer-lived. Had these titans died as black holes instead, the cosmos might have remained a darker, chemically barren place. Their self-destruction was the universe's first act of recycling, a sacrifice that lit the way for everything that came after. Long before the first stars flickered to life, the universe was humming with sound. Not the kind we hear, but colossal pressure waves rippling through the searing hot plasma of the early cosmos. These primordial vibrations, called baryon acoustic oscillations, left an invisible blueprint in the fabric of space, guiding where gravity would later gather the raw materials for the first starlight. Picture a stone dropped into a pond, sending out concentric rings, except here, the pond was the entire universe, and the ripples were frozen in time as space expanded, leaving ghostly fingerprints in the distribution of matter. These oscillations began just moments after the Big Bang, when the universe was a roiling soup of particles and radiation. Photons and baryons, protons and neutrons were locked in a violent tug of war, with radiation pressure pushing matter outward while gravity pulled it back. This created rhythmic compressions and rarefactions, like sound waves moving through air. But as the cosmos cooled and atoms formed, the photons raced away, leaving the baryons clapped in place at the edges of these cosmic sound waves. The result, a subtle pattern of alternating dense shells and sparse voids, all precisely spaced about 500,000 light-years apart, a cosmic ruler etched into the universe's structure. When the time came for stars to form, this pattern became destiny. Dark matter, already clumping along the denser regions of these oscillations, dragged hydrogen gas with it like an invisible scaffold. The first protogalaxies didn't appear randomly. They blossomed at the crests of those ancient waves where matter had been piled highest billions of years earlier. Imagine tossing seeds onto a corrugated roof. They'd naturally collect in the grooves. Similarly, the first stellar nurseries clustered along these preordained ridges, their spacing echoing the original wavelength of those primeval sound waves. Modern sky maps reveal this legacy. Surveys of millions of galaxies show a faint but unmistakable preference for pairs separated by the same 500 million light-year scale, a fossilized echo of the universe's infancy. Even the Milky Way's position isn't accidental. We likely sit on the remains of one such density peak, a descendant of structures shaped by vibrations from a time before time. The first stars didn't just light up the dark, they danced to a rhythm set in motion when the cosmos was younger than a heartbeat. What's astonishing is how enduring this pattern proved. Supernova, galactic collisions, and the relentless expansion of space have blurred but not erased it. Like finding the outline of a prehistoric city beneath a modern metropolis, astronomers trace these oscillations through statistical shadows. The slight overabundance of galaxy pairs at specific separations, or the way quasars' light dims when passing through gas clustered at predicted intervals. These are the universe's oldest surviving structures, more permanent than mountains, more ancient than starlight. Yet the real marvel lies in the symmetry. Those oscillations didn't just influence where stars formed, they dictated the scale of cosmic architecture itself. The voids between galaxy superclusters, the web-like filaments of dark matter, even the average distance between stellar nurseries in the early universe, all bear the imprint of those primordial sound waves. The first starlight didn't break the silence of the cosmos. It emerged from a harmony written into existence when the universe was a symphony of plasma and light. Discovering the origins of the first stars isn't just about rewriting astrophysics textbooks, it's a profound shift in how we see our place in the cosmos. For centuries, humanity's origin stories were rooted in myth and tradition, confined to the boundaries of our planet. But the revelation that we're literally made of stardust, that every atom in our bodies was forged in the hearts of long-dead stars, collapses the distance between the vastness of space and the intimacy of our own existence. This isn't just science, it's a philosophical revolution, one that redefines what it means to be part of an ancient, interconnected universe. Consider the cultural weight of this realization. Across civilizations, stars have been deities, guides, and symbols of the eternal. Now we know they're also our ancestors. The iron in our blood, the calcium in our bones, these elements didn't originate on Earth but in the cataclysmic explosions of stars that died before our solar system was born. Indigenous cosmologies have long spoken of a living, generative cosmos where humans and stars are kin. Modern astrophysics, in its own way, echoes this wisdom, revealing a material continuity between the heavens and ourselves that transcends myth and enters the realm of measurable truth. Yet with this knowledge comes responsibility. If we're the universe's way of understanding itself, as Carl Sagan famously suggested, then our study of the first stars isn't neutral observation. It's an act of cosmic self-discovery. The telescopes we build, the simulations we run, even the questions we prioritize in research, these choices reflect cultural values as much as scientific curiosity. Who gets to define humanity's relationship with the cosmos? Which voices shape the narrative of our origins? The answers influence everything from education to space policy, determining whether this knowledge unites us as a species or becomes another wedge between cultures. There's also the haunting question of rarity. The conditions that allowed the first stars to form the precise balance of dark matter density, hydrogen abundance, and quantum fluctuations were so finely tuned that even slight variations might have left the universe forever dark and lifeless. Recognizing our existence as the product of such improbability could inspire stewardship, a sense that we owe it to the cosmos to preserve the rare conditions that made us possible. Or it might feed existential anxiety, underscoring how fragile our place in the universe truly is. Perhaps most striking is how this discovery reshapes time itself. Human history spans mere millennia, but the story of our atoms stretches back over 13 billion years. We're latecomers to a narrative that began when the first stars lit fires in the dark, and our chapter is still being written. This perspective humbles nationalism, borders, and even anthropocentrism, suggesting we're not the center of the universe but participants in an unfolding story far grander than any single species. The ethical implications ripple outward. If we're stardust become sentient, what obligations follow? Do we owe something to the universe that birthed us, perhaps by ensuring life endures beyond Earth? And how do we reconcile this cosmic kinship with the damage we've inflicted on our own planet? The first stars didn't just illuminate the universe, they lit a mirror, forcing us to confront who we are in the grand scheme of existence. Their light reaches us not just as photons, but as a challenge to recognize our shared ancestry with the cosmos and act accordingly. From the infinite dark sprang the first light, not as a single spark, but as countless fires igniting across the void, each one a rebellion against the emptiness. These were more than just stars. They were the universe's first alchemists, turning hydrogen into helium, helium into carbon, and carbon into the very elements that would one day become planets, oceans, and living things. Their legacy isn't just written in the distant past, it's in the marrow of your bones, the air in your lungs, the screen glowing before your eyes. Every heavy atom here was once part of a star that lived fast, died young, and scattered its essence across the cosmos like seeds in the wind. The scale of this inheritance is breathtaking. The gold in a wedding ring forged in a supernova's heart, the oxygen fueling your cells, a gift from a star that perished billions of years before Earth existed. Even the silicon in computer chips traces back to stellar explosions so violent they outshone galaxies. But their greatest gift wasn't just material, it was structure. Those early stars didn't merely illuminate the dark, they built the gravitational scaffolding for galaxies, their death seeding the nurseries where new stars would form, each generation smaller, steadier, and more hospitable to life. What's astonishing is how fragile this chain of events was. Had the first stars been slightly less massive, they might not have reached the temperatures needed to forge carbon. Slightly more massive, and their explosions could have sterilized entire regions of space. The balance was exquisite, a cosmic tightrope walk where the conditions for life depended on stellar lives and deaths playing out precisely as they did. We're not just observers of this story, we're its living continuation, the universe's way of turning starlight into curiosity. So when you look up at the night sky, remember, you're not just seeing distant suns. You're glimpsing your own cosmic ancestry, a family tree written in fusion and supernova, and the story isn't over. Beyond the stars we see lie mysteries still untold, ghostly remnants of the first black holes, unseen threads of dark matter, perhaps even other worlds where stardust learned to wonder about itself. The first stars lit the way, but the next chapters are ours to write, question by question, discovery by discovery. After all, the universe didn't wake up just to go back to sleep. It woke up to keep looking, and so should we.